And welcome to our class today. Um, on Monday, as I told you already, we will spend most of the time practicing what we learned in class. And today I would like to start with one problem from chapter 1, our point kinematics problem. And then we will do in the second example, a second exercise, from chapter 2, rigid body, so that you have the comparison between these two and just to remember the approach for the two different types of problem. So for the exercise in our online class, I will open breakout sessions and you can choose your breakout session on your own. And then I will go through the breakout sessions, ask whether there are questions, problems, difficulties, whatever. And then please talk to me and tell me everything's fine or you're stuck somewhere maybe, then I can try to help. And you can also try to share your screen if you are writing on a computer as well, or you could just use your camera and hold your sheet of paper into the camera, and then I can try to read this and help you. And if you have a question and I'm not there in this moment, you can call me into the session as well. So, but for the problems, it's really important that you try to solve it on your own or in your small group with classmates and not just wait for my solution. Okay, we will start with the first problem, exercise 112. Let's have a look in the my notes. Okay, so there it is. We have a handling robot, and it's very similar to our very first example of problem of chapter 1, where we discussed the basic approach to these type of problems. So here we have this handling robot with two rods connected by a joint. There's a clamshell, and we want to describe the motion of the clamshell. The lengths are given of both rods, L1 and here L2. And the lower rod moves with given angle, angular velocity, and angular acceleration. And the second rod as well. The variables are given, angle, angular acceleration, angular velocity, but no numbers are given. So we have to find velocity and acceleration of the clamshell in general form, meaning dependent on the variables given. Okay, first step to do is drawing the figure. Please draw two figures, one for velocities and one for the acceleration. And keep in mind that this is a point kinematics type problem, or at least we are using our point kinematics approach here to solve this problem. And then we have to describe one point on two different systems, our leading and our relative motion, leading system, relative system. And we are describing the clamshell. So this point right here. Okay. Okay, I will open the sessions. Just take some time to choose your sessions with your friends, with your classmates, and then try to draw the diagrams. And in about 10 minutes, I will all call you back into the main room to discuss the diagrams. And then we will start solving. If you're faster, of course, you can already start solving the problem as well. Okay.
Does anyone know how to solve it?
Okay, let's have a look at the figures. On the left, we can see the figure for the velocities, which is quite simple, of course. The first thing we have to do is we have to decide which one is our leading and which one is our relative motion. Since we already discussed this example in class at the beginning of chapter 1, I think it's clear our leading motion is the rotation of the first rod with length L1. And the motion is a circular motion. It rotates about the hinged support with given omega-1, alpha-1. So for describing the leading motion, we are freezing the relative motion, meaning that there's no other motion. We have a rigid connection between those two rods, and we describe the pure rotation, the pure circular motion of the first rod about the hinged support. Our velocity vector of the leading motion has to be perpendicular on the path and perpendicular to the radius, tangential on the path. And that's, according to our color coding, the purple vector V index L for leading motion. So the radius of the circular path is the distance between the hinged support and the clamshell. This line that I drew here, that's the radius of the circular path. That means this is our distance. And of course, it's time dependent. It's a time dependent radius. The radius of the circular path of the leading motion changes over time since we have this angle phi 2, which changes over time as well. So we have the leading motion vector perpendicular on the radius, and for the acceleration, we have tangential and normal component, again, perpendicular to the radius, tangential on the path, and the normal component points towards the center of the circle. For the relative motion is the rotation of the second rod, L2. And for this motion, we are assuming that this is our only motion. We are standing on the moving object, on the leading motion, and we see the circular motion about the joint. And here, the velocity vector points perpendicular on this radius length L2, tangential on the path. And again, we have tangential and normal component of the acceleration. And then, since our leading motion is a circular motion, we have to consider Coriolis acceleration using the right-hand rule, thumb as axis of rotation of the leading motion, index finger as direction of the relative velocity, results in the middle finger indicating the direction of the Coriolis acceleration, pointing in direction of the normal component of the relative acceleration. Okay, any questions so far?
Professor, I have a question.
Yes.
Why our acceleration and speed for the leading motion are not perpendicular to the first rod, but perpendicular to the line between the start and the clamshell?
Because they have to be perpendicular to the radius of the circle. And if this is our leading motion, looks like this, rigid connection here, okay? And we describe this motion, and now the system rotates. Then sometime later in time, it might be here, this object. Then this is the circular path being described by our clamshell. And then this is the radius. This is the radius of the circular path and not this. So we have to use the radius, the distance from our hinge support to the clamshell as our radius of the circle, and then the direction of velocity and acceleration follow from that.
So basically, we are not very interested in the first rod at all in this case.
No, we want to describe the clamshell and not the motion of the first rod.
Okay.
Okay.
Thank you.
Yep.
Is this Coriolis same as the centripetal?
I didn't understand you, sorry.
Is the Coriolis acceleration same as the centripetal?
The Coriolis acceleration is the same as the centripetal acceleration?
Yeah.
Yeah. The Coriolis acceleration is a pseudo acceleration that only exists because our moving observer stands or is traveling along a circular path. And there needs to be an acceleration keeping him on track. So in difference to a rectilinear motion on a circular motion, there needs to be an additional acceleration, or then later on a pseudo force, inertial force, to keep him on track. And that's where the Coriolis acceleration results from. Okay. Now we need to compute the radius, RT, the radius that changes in time, to describe our variables, to solve our system. And we also will need an angle, the angle between the vectors. And we have this triangle here. We know the angle phi2. We know the length L1 and L2. We are interested in the radius. And then we need another angle. Let's call it gamma, this angle right here. And now for this triangle, we can use the law of sine and law of cosine to determine the different variables. There was quite a similar problem in Engineering Mechanics 1 with the boat and the two smaller boats carrying or pulling the boat in a direction, for example, where you had to use these laws as well. It's just simple math. Well, let's start with the law of cosine. So for the law of cosine, we can find the length r by building the square root of L1 square plus L2 square minus 2 L1 L2 cosine phi 2. Okay, of course, we have to leave it like this. There are no numbers given. So now with this equation, let's simply assume or state that we know the radius, and we can use the radius later on in our computations. There's a question referring to the Coriolis direction of the Coriolis acceleration. Use your right hand. Now, what is the direction of omega 1? Omega 1 points counterclockwise. So your fingers have to point in direction of omega 1. Your thumb points upwards out of the plane of paper. Your thumb points upwards. And now use your index finger and rotate your hand until your index finger points in direction of the relative velocity. And now if you have that, use your middle finger. They are all three fingers are perpendicular to each other. Use your index finger, and the index finger indicates the direction of Coriolis acceleration. Okay. Then for the angle, we use law of sine. Then the angle gamma is equal to the arcus of sine from L1 over R sine index finger is always relative velocity, yes. Thumb is always leading omega. It's always the same. Okay, of course, again, here we cannot compute anything. We have to leave it like this. But now for our computations, when we derive the variables for leading and relative velocity and Coriolis acceleration, we can use R and gamma. And then in the last step, we can do the vector addition. We will not substitute R and gamma in this exercise because it's just a really long equation, and it makes it really difficult to read. So just keep R and gamma in your following equations that you will state now. So next step, after deriving the figure, as I already said, derive the velocities and acceleration components as drawn in the figure, and then build the absolute velocity and acceleration using vector addition. Okay, I will open the breakout sessions again. There are a lot of students in room number 1, so maybe it would make more sense to use the other rooms as well. So I don't know if you can see, but for example, room 5, room 6, room 8, and 10 are empty. And then in the other rooms, except of room 2, there are very few students as well. And now I will try to go through all the sessions, through all the breakout sessions, breakout rooms. And if you have a question, please ask. And even if you're staying in the main room, just write something in the chat or talk to me. But when I'm not in the room, I will not read what you write in the chat. So if you write something to ask me, make sure I'm in this room that I can read it, okay? All right, let's get started.
Hello.
I kinda came in late, so I'm not sure what's happening.
We're doing the exercise
112, right?
1-12, yeah. She already gave the diagram, she already gives like the law of cosine and law of sine. So what we need to do is derive the leading motion, relative motion, Coriolis acceleration equation, and the absolute equation.
Interesting. Yeah, this is tough. I don't think I'm gonna be doing the exam until I finish the fundamentals and the statics.
Yeah,
There are many things.
I couldn't hear you. Can you say that again?
I think I'm gonna do the exam after I finish fundamentals and statics, because there are many things from these courses that I haven't really caught on to.
Fundamentals, you mean like the mechanical design from the first semester?
Mech design.
No, this have nothing to do with the.
Yeah, but it has to do with statics.
Yeah, it has to do with statics, and statics had nothing to do with the first semester.
Yeah. So everything adds up to one another.
Okay, okay. Zane, when are you coming to Germany?
Hopefully soon. Still in the talks with the embassy. Practically everything is done. I've sent them all the documents. Just waiting now. Waiting on them. They're super slow as well.
Mm-hmm. I think I can try to share my screen.
Courage, at Zane.
This is room number 6, is it? Number 4.
This is room 4.
Share screen. Okay, if I make a mistake, please let me know, because I don't know. Hmm. Anyone have any ideas for the relative motion?
No.
Can you repeat your question, please?
We get what?
Repeat the
What was
question.
your question?
Anybody have any ideas for relative motion? VL is omega 1. I thought it would be oh yeah, I wanted to write omega 2 actually. Where is it? Omega 1? Omega 1. Yeah, I think it's probably omega 1, yeah. What but why is it omega 1?
Omega 1 for the leading, because it's the first arm.
Okay.
Check the picture from the question. Yeah.
I see. Okay.
Hello. How are you doing? Are there any questions?
We are trying to derive the equations for relative motion.
Okay, yeah, perfect.
But so far, is the leading motion correct?
Yes, it's correct. But you still need the tangential component of the acceleration, ALT.
ALT.
The tangential acceleration. You do not have to memorize the equations. It's would be fine to simply look in the formulary. Look it up.
Professor, is the leading motion correct? Should it be omega 1, L2, or the
No.
radius R of t?
Yes, it's R of t. That's right. It's not L2. It's the radius of the circle that you have to use, the radius of the circular path being described by the motion.
So
Yes.
this means that L1 does L1 does not actually count. What counts is
Well,
the radius from the origin to the point mass.
yes, but L1 is part of the radius, of course.
Yeah, we use it to derive
but
R of
yes,
t.
but you do not have to use it directly. You always have to use the straight line between your point of interest, clamshell in this case, and your hinged support, your point of rotation, the middle of the circle.
Okay, one more question, Professor. Yeah, this problem, we are only interested in a point mass of maybe 2 connecting rods. Like what we have been doing in class is either 1 connecting rod or 2 connecting rods. Can we also extend this idea to maybe if we have a point mass and from the origin to the point mass, we have like 3 connecting rods in between the point mass and the origin, or maybe multiple connecting rods. Can this idea be extended?
Yes, of course. We are sticking with 2 to keep it relatively simple, but of course you could extend it to several rods and masses.
The last exam, I don't know what it was like. The idea was extended beyond just 2 bodies.
No, it was actually in the last exam, it was exactly this problem here.
Yeah, because we have a sun, a sun that is static, and a rod from the center of the sun to another.
I even drew this.
Body.
Yes, I even drew this free body diagram like this in the cheat. You had this problem with the sun and the planet, and then which was nothing else than these 2 rods being connected, and then I drew just the rods for you to realize that it's this problem that I'm referring at. Yeah, but a lot of students didn't see it. I don't know.
Yeah, it has a lot of thinking behind it, because what we actually did in class is because the sun has come in and another circular body has come in, and we need to find the kinematic relations and all. So, of course, there's a lot of thinking behind it, and especially for me, it threw me off, and I couldn't realize, and the time was really short. So,
well, yeah, that's probably a problem of practicing more if you have time issues, because the problem itself was just like this. You had to simply derive the same equations we're doing here right now, and then you had the part of the forces where you needed kinematic conditions. So yeah, that's just practice. We have later on in the next chapter several problems discussing kinematic conditions.
Yeah, I solved all the exercises before the exam last semester. Honestly, I did, but it's not an excuse anyway. My question now is, and what I'm really interested in is, how far can we actually extend these ideas? So that is now what I am interested in, not just to solve the problems in the exercise and just stick to the scope of.
Well, how far you need it to extend, right? But if you do not do that in class, it will not be part of the exam. So if you're thinking of the exam, but of course, if you have a different problem and a different subject or in your internship or whatever, you can extend this idea.
Yeah, but this is not very easy to extend it during the exam, because we have 4 questions and we just have.
No, we did not extend this problem in the exam. It was a different question added, but it's not there was no 3rd rod added to the system.
Okay, it's fine. All right.
We're just 2 rods in a joint. Okay.
Hello, Professor. Okay. Okay, so does anybody know what are we supposed to write for ALT? I think it's
ALT should be alpha 1 times R of t. Yeah, then okay, you've gotten the normal acceleration already. Yeah.
okay. So
Then the Coriolis acceleration should be yeah, okay, someone has written it in the chart.
is it like that?
Yeah, I think that's what I wrote. Yeah.
Then but why? I actually don't really understand. What's next? We need to, I think, is there any, I think we need to find the absolute equation, absolute values. Is it?
Yeah, so the acceleration, you have tangential and normal components. And then the
Yeah, you have is for acceleration to the equation for accelerations. And if you need to resolve acceleration, because you need to find acceleration. Then I think that you need to have 4 equations for acceleration.
I think we need to choose a coordinate system that we can resolve all the components to. Then when we choose the coordinate system, then we can then resolve the other components to that coordinate system. Then we can find the absolute velocity and acceleration.
also, I believe for the relative acceleration, We no longer want to use the R of t. We want to use L2. I'm pretty sure.
I'm so sorry. I have no idea what you guys are talking about.
For the relative what? Relative velocity?
Yeah, so for the relative acceleration, let's think, and the relative velocity as well. We want to replace the R of t with L2.
Yeah, that's correct.
Replace the RT with L2.
And we're doing that because we aren't considering the motion, the velocity and the acceleration of the whole system. The relative velocity and acceleration are from the end of the first rod. So I guess that's the beginning of the second rod to the end of the second rod, so rather than the whole thing. Anyway, after we get the relative velocity and the relative accelerations, we should then be able to sum everything up to get our total velocity and total acceleration. Well, unless the question didn't want us to do that, let me read it again. Yeah, so I think it wants the total.
We need to have been fine. I think we need like
Because for the
we need 4 equations, right? And so far we have 4 acceleration. Should we summon the professor? And the following acceleration. Yeah, I think we have to do that. Oh, I have no idea how to do that.
There's a question. You have a question here?
Professor, how do we proceed?
Well, derive the variables for the relative motion, relative velocity and tangential component.
The equation for the relative velocity. So I should
Just on your right. Step 2, actually, relative motion. You already started. ARN is there, and you need ART and VR. No, not the tangential, not time dependent.
Oh, you said
R and T, same as for the leading motion. Just now we are in relative motion. Yes. No, alpha. All these, you do not have to memorize the equations. They are all in the formulary. So just look them up. Don't try to memorize. You don't have to memorize them. Okay. Alpha 2, L2 in this case. And the relative velocity. You need, for every vector that you draw in your diagram, you need an equation for the 2 velocities and for 5 accelerations.
And then in order to sum the velocities and the accelerations,
Exactly.
do we need to break them into components?
Yes, but that's the next step. First,
Okay.
you need the absolute value. So it's not a vector here, VR.
Mhm. Okay.
Simply VR is equal to, and then just copy what you have for the leading motion. Just transfer it to the relative motion. Then it's omega 2, L2. Just like that. Yes.
Okay.
And then you have Coriolis acceleration, the equation for the Coriolis acceleration. Yes, okay. Then you can substitute VR such that it depends on the values given. And it's not omega 2, it's omega 1, leading angular velocity to omega 1 times VR. Yes.
So this would be
Yes, exactly. Okay, and so first step, drawing the diagrams. Second step, deriving this equation. And then third and last step, building the absolute velocity and acceleration. And now you have to decompose it into vectors, to 2 components, and sum them as we did last time. So for example, for the velocity, it's the absolute velocity is the square root of the sum of the components in, I don't know, relative direction plus the direction perpendicular to it. Now here, in the previous examples, our vectors were always perpendicular to each other, like in the merry-go-round that you have right here on the side. And here in this example, they are not perpendicular. So leading and relative motion are not perpendicular to each other. There's an angle in between, the angle gamma.
Mhm.
So you have to decompose at least one of these vectors depending on gamma. For example, for the velocity, you could build the sum of the direction in VR. Then you'd have to decompose VL, leading velocity, into one component parallel to the relative velocity and a component perpendicular to the relative velocity.
Mm.
Yeah, we will have a look at this in a few minutes, because I think that's the part that causes most difficulty.
Okay.
Okay, but you can try to solve it. Okay, so what you had to do was simply stating the equations that are written in the formulary on your paper for the specific example given. So dependent on the specific lengths and angular velocities and accelerations. So in our case, we have leading motion, relative motion, Coriolis, acceleration, and all the components exist, nothing is zero. And these are the equation: angular velocity times radius, angular acceleration times radius, etc. So we have to make sure for the leading motion that our radius is this r that we just computed using law of cosine. And for the relative motion, our radius is the length of the second rod L2. And then that's it. First step, drawing the diagrams. Second step, deriving the equations without computing anything, simply deriving or stating equations for every vector that we drew in our diagram. And then the last step is building the absolute acceleration and absolute velocity. Could you please explain the velocity? Well, no, the velocities do not depend on my fingers, on the direction of fingers. The velocities are always perpendicular on the path, tangential on the path, perpendicular to the radius. So for the leading velocity, the radius is the distance from our point of rotation to the point of interest, the clamshell. So the r, find we have dependent. So the velocity vector is perpendicular to this radius. And for the relative velocity, it is perpendicular to the radius of the circular path of the relative motion. So the joint, sorry, the joint between L1 and L2 and the clamshell. So the length L2 is the radius here. Okay. For the absolute motion, I think this causes some trouble, or caused some trouble for several students, because now our vectors are neither parallel nor perpendicular to each other. So we have to decompose according to directions that we can choose. So what we have to do first, have to know first, is the angle between these two vectors, between leading and relative motion. And that is gamma as well. Well, yes, but we are not talking about forces yet. We are only talking about velocities and accelerations. But yeah, if you're able to derive them correctly, draw your diagram correctly, including velocities and acceleration, then it's simple. But again, our velocities on a circular motion are always perpendicular to the radius, tangential on the path. So there are not that many options that we have to draw these forces. I'm talking about forces as well, to draw these velocities and accelerations as well. The tangential component is tangential on the path, and the normal component points towards the center of rotation. Okay, yeah, but once we have the diagrams, it's just standard procedure, simple math. Okay. Now here for the velocities, let's derive the. Have you been here at the beginning of class? Derive the absolute velocity. In general, it's the standard vector addition, leading plus relative velocity. I did draw this figure. Leading motion. That's our starting position. Then sometime later in time, it's here, and then it's here, etc. So this is the circular path our object, our clamshell follows. So the radius, this is the radius. The radius of this circular path is this one. That's the radius of the leading motion. Assuming that we have a rigid connection here, no joint, no motion here between L1 and L2, it moves like this. And then this is always the radius. And the velocity depends on radius and angular velocity. That's how we find, or we have to determine the radius. Okay. So always, maybe it helps just drawing several positions of your objects to find which one is the correct radius. Okay, vector addition. We have to decide which is our which two directions we want to choose. So it would make sense to either choose the direction of the leading or the relative velocity vector. It doesn't matter which one. I will choose the relative vector. So let's call this X and Y direction. And now for the vector addition. It's the square root of all vectors pointing in X direction. This one right here. Then we have VR, and we have a component of the leading velocity. So it's plus VL cosine gamma, and then the square of that. Because our system moves with omega 1. The whole system rotates with omega 1. There's no other leading angular velocity. So that's the motion. The only thing is we are assuming that we are freezing our relative motion, so this connection is fixed, and we are describing this point. But this point moves along the circular path with omega 1. Okay. And then, okay, so that's X. For Y direction, we only have to consider the component of the leading velocity, VL sine gamma. And that's it. Since we do not have any variables given, we have to leave it like this. Gamma. The angle is called gamma. This one, yeah, gamma. Okay, so we have to do the same for the accelerations, but of course here we do not have only 2 vectors, we have 5 vectors that we have to take into consideration. But again, we start with our standard equation, our standard vector equation, leading acceleration plus relative acceleration plus Coriolis. And relative acceleration consists of 2 components each, normal and tangential. I will use the same coordinate system as above. Then we have the normal component of the relative acceleration. We have the Coriolis acceleration, and we have components of both leading accelerations. ALN cosine gamma plus ALT sine gamma. Square root. That's, oops. I started with Y direction. And to move it up a little bit, plus AR tangential minus ALN sine gamma plus ALT cosine gamma. And that's the x direction. Okay, and I think this might be the most difficult part of the problem. Deriving or decomposing the vectors according to the angle. But then you have to make sure that you get the angles right. If you know gamma, then where can you find gamma again? That it's between these two velocity vectors. And once you have that, you have to choose your directions, x and y direction, your coordinate system, and decompose the vectors according to your coordinate system. The part above, the second part after drawing the diagram, is simple because you simply have to state the equations from your exercise book. From your formulary. And that's always the same. You only have to make sure to use the correct angular velocity and acceleration, correct indices, and correct radius. But it's a possibility to gain a lot of points easily in the problem. Okay, any questions?
Professor,
Yes.
why do we vary the radius as a function of time? I think I'm thinking the radius varies as a result of when phi2 is changing, then the radius changes. Why do we vary by time?
Well, because phi2 changes over time. It's at the beginning when we start to describe our object. It looks like this. Oops. And then this is the radius. And then later on, it might look like this. And this is our new radius. And then even later in time, it might be maybe here. And then this is the radius. So the radius changes over time since our angles are time dependent. The angles change over time. Then the radius has to change over time as well. T0, T1, T2, and so on. Okay.
Okay, yeah.
Are there other questions?
Yes. So I've chosen a different coordinate system according to the leading motion. So is there a way that I can check my answer?
Well, in general, it doesn't matter. Your coordinate system, I'll draw it here, looks like this probably, right?
Yeah, yes.
Yeah. So you have the full tangential component of the leading motion in one part and the normal component in the other. And you had to decompose these three vectors. And then again, these are our angles, gamma. Then if you, well, I'll write it for this direction only, okay?
Yeah.
Then you'd have AL tangential, then we would have AR tangential, and then if you draw it a little bit bigger here, that's our purple component, and we are decomposing this vector into, well, I will use red, okay, but into these two components, right? There's the right angle. And here's gamma. So it's AR tangential, it's the adjacent angle, then it's cosine gamma, and then for the normal and for the Coriolis acceleration, it's the sine of gamma. And they also point, that's ARN, and we decompose in these two components, so they are also positive, ARN plus a Coriolis sine gamma. And for the other direction, instead of, you have to simply change cosine and sine, swap them. Oh, yeah, exactly. And then ALN would be the other direction. Okay, other questions? Okay, if there are no more questions, I would like to have a quick look at an exercise from chapter 2. We will not, of course, we don't have the time to fully solve this problem, but we can talk about the free body diagram, our diagrams, including velocities and acceleration. So it's problem 2.5. So we have a crank drive of a combustion engine, and that performs an oscillatory motion. And we have the crank radius with 40 millimeter and in constant angular velocity, important, it's constant angular velocity of 200 per second. Then the connecting rod has a length of 160 millimeter. That's this distance K set. That's our connecting rod, okay? It has a distance of 160 millimeter. It's rotationally mounted by the crank pin and crank web, with the crank web. And the other end is rotationally mounted by the pin in the piston here in K. And the piston, as you can see from the figure given, can only move horizontally. It's also stated in the text. And we have to find the velocity and the acceleration of the crank pin and the velocity and acceleration of the pin K. So velocity and acceleration of point Z and point K. And at the given angle of 60 degrees. So now this is an example with numbers. I know it's usually you prefer exercises with numbers because it's easier to compute, to obtain values and not just long equations. And but the procedure again is the same. Now we will describe this system as a rigid body. Our rod, distance KZ, is a rigid body, and ZM is a rigid body, a beam, a rod as well. And what we said for these type of problems is that we describe the problem as translation plus rotation. So for example, well, we will have a look at different options to solve this problem. Let's call it option 1. Now, we will describe point K. So we will say K moves translational as Z, 2 points on one rigid body. That's the important fact to remember for rigid body problems. It moves translational as Z, and at the same time, and K rotates about Z. Meaning for the velocities, Pk is equal to Vz, translation of Z, and at the same time, K rotates about Z. Indices Kz means K rotates about Z. First point rotates about the second point. Same equation for the accelerations, of course. Okay, and then once we decided which point we want to describe in dependence on a second point, we can derive our diagram, our drawings from that. So we do not have to draw everything around it. The important thing is to draw these 3 points, K, Z, and M. Okay. K, Z, and M. That's R, that's L. And that again is some distance Q, for example, since we already used R. The true system in the true system K doesn't rotate. No, of course, K moves translational, but we assume that we can describe this motion, which is only in horizontal direction back and forth, as rotation plus translation. No, it cannot be Vz plus what you just wrote in the chat is wrong. What you could do is write it like this: Vk, and then it had to be Vzk, not Kz. Okay, your indices have to match. But of course, that we could also do. This will be our option number 2. But what I want to say is it doesn't matter whether the point really rotates or not. It's just our standard procedure, our standard approach. And for any arbitrary system, we can use this approach. I will give you a simple example which might help you understand what we do. Let's assume we have a wall and there's a ladder standing here. And now there's a person, it's like a problem from statics actually, but assume there's a person walking on this ladder and the ladder starts to slide. What it will do is this: it will slide downward and at the same time backwards. And then this might be a position later in time before the ladder hits the ground. Now, we are not able to describe this motion of the ladder like this because it's not a simple rotation and it's also not a simple translational motion. But what we can do is we can say, okay, this absolute motion consists of like this translation, like this point right here, translation downward. Then the entire ladder would be here, translation, and then we add rotation. And we say, okay, and this ladder rotates about this point. And if we do the translation first and then add the rotation, we end up to our absolute motion. Even though, of course, this point here, I think this is A and this is B probably, this point here cannot move into the ground. That's just not possible. But mathematically, we can describe the general motion as translation plus rotation, and we end up with the real motion, this general motion, red, okay? And that's what we are doing for every example in chapter 2 and later on as well, of course. So what I mean is it doesn't matter how the point moves, really. And even if our point Z would perform a pure rotation, which it does actually here, we can still assume it as our rotational component of point K. That's just our mathematic approach, standard procedure. Okay, and it works for any type of problem. Okay. 5 minutes, 10 minutes left. Okay, let's try to draw the velocities for this diagram, leading and, well, not leading, translational and rotational motion. Yes, the problems always need a figure. With the problems, obviously, there is a figure given in the problem description, and then you have to draw your own figure with everything that's relevant to solve the problem. But from the text alone, you would probably not be able to derive this figure, of course. Okay, now just I'll give you 5 minutes to draw the velocities for this. And then without breakout sessions, of course, there's not much time. Yeah, I don't know, is this class called Engineering Mechanics 3 for you? Because for me, it's still called Engineering Mechanics 2. And that's okay, draw the velocities. Okay, yeah, thanks. Okay, let's have a look at the figure for the velocities. Now, our point Z moves on a circular path. It's a pure rotational motion. And then our velocity of Z, absolute velocity, looks like this, Vz, perpendicular to the radius. Now for point K, we are assuming that K moves translational SZ. then this would be our translational component, vz. And at the same time, k rotates about z. So if this point z is moving upwards, k moves forwards, and then the direction of the rotation is this omega. And vkz points perpendicular to the distance kz, length L, with vkz. And of course, we do know the direction of the absolute velocity of k. That has to be horizontal, like this. Okay. There's an angle given. Any questions so far? Okay, great. Then,
excuse me, the letter in the bottom is a Q, right?
That's a small q. That's an M here, and that's a Q.
Got it.
But of course, you can choose any other, but we already use L and R, and then I use Q. Why? V2, VZ, because it's given here. The direction of rotation is given in the figure provided. And then the velocity has to point perpendicular to the radius and tangential on the path and in direction of travel. Yeah, okay, okay. Kz is the rotation of k about z. These indices always refer to k about z. K rotates about z. Okay, that's why it's important to have that in correct order. It's not that z rotates about k. In our case, k rotates about z.
Professor, is the purple one also VZ?
Yes, they are the same. Just
Okay.
we said the red we said is the absolute velocity in point z, and for point k we said is the translational component.
Okay.
Okay. Okay, any other questions? K does not really rotate about Z. It's just an assumption, like our mathematical approach. Of course, K moves horizontal, but due to superposition of translational and rotational component, it ends up to a horizontal motion, sums up to a horizontal motion. In our case, we start with K and Z like this. And then later in time, Z might be here, K might be here. Okay, it might be here. Then this is the direction of rotation. Exactly, that's why I wrote option 1. We will discuss 3 different options, okay? Okay, so it's already 1:15. So we will stop at this point and continue here in our next class. So have a good week and see you on Friday. Bye.